Okay, so let's start with lecture 2. Video. Okay. So last time we did something about system of linear equations. So let me recall that for you. So we talked about something called the system of linear equations. So we were given a bunch of equations. And we also talked about the number of solutions to a linear equation, or sorry, the system of linear equations. Then we also talked about so-called the row picture and the column picture. Okay. So these are the three things we talked about. We started with the system of linear equations. We talked about the number of solutions a system might have, and we saw that a system could have no solution, it could have exactly one solution, or it could have also infinitely many solutions. Then we saw two ways of looking at the same system of equation. One was the row picture, where we looked at it in terms of rows. And the same set of equations can also be viewed as columns or column picture, where we saw that the right hand side has to be expressed as a linear combination of the columns in the coefficient matrix. So with this setting in mind, let's try to get introduced to some terminology. There are two types of things that we want to associate, first of all, with system of linear equations, and those two things will tell us the existence of solutions. Okay, so let's try and see what do we want to get introduced to. So there are two things that two terms rather, that we would like to introduce. One is the so-called consistent system. And the other we will call as the inconsistent system. Okay. The consistent system means the system will have at least one solution. And the inconsistent system means our system has no solution. So if you recall, when we had the case of parallel lines, then we did not have any then we did not have any solution when the two lines did not intersect or two planes did not intersect. And whenever we had an intersection of two lines, there was a system where we had exactly one solution, and there were times when the two lines were on top of each other, so we had infinitely many solutions. Both those systems are called consistent systems because we are guaranteed to have at least one solution. Okay, so let me start with a simple example of a system. So let's say we have x plus 3y is equal to 4 and 5x minus 4y is minus 7. Okay? Remember what we did? We said suppose we have a system of equations like this. We can write down a matrix for it, so-called augmented matrix. So remember, we had a coefficient matrix and we had a right hand side vector. The line separating tells us the left side is the coefficient matrix and the right side is the constant vector. So this we called as the augmented matrix. Now our objective was to somehow row reduce it. I introduced this term without telling what exactly this entails. So the idea is to row reduce it to a nice form, a nice matrix, which perhaps may look something like this, which has some bunch of zeros and ones. These entries could be something. So this is what we had called as our dream matrix, but later on I introduced a term. I had called it, or we will call this as our row echelon matrix. So something like this we will call as a row echelon matrix, and we'll see if we can achieve this nice form. Because once we achieve this nice form, we will be able to see one thing, that this nice form helps us identifying the solutions or writing down the solutions fairly quickly. So now the question is, how do I start from here and go up to there, and what exactly do I mean by row reduced or row reduction? Now there is one more question which is important, and at this stage we should ask ourselves, whatever this row reduction business is it always possible for us to start from an augmented matrix and get this row echelon form or a nice form which looks like that? Does every matrix have this reduction possible? Now to answer those things, first we have to get introduced to what exactly do I mean by row operations. So actually I shouldn't have erased it, so let me just bring it back. So let me just rewrite this system, because I use this system as an example for us to do things. Now remember, we are interested in trying to find the solutions to this system of equations. So that means whatever we do, we have to ensure that at no stage the solution set should get compromised. In a sense, suppose I change the name of the variables from xy to ab, and would you agree that there will be no change in the system of in the solutions for this system just because I changed the variable name? Moreover, what if I swap these two equations? Suppose I write this equation first, 5x minus 4y. So suppose I swap it. So I write 5x minus 4y equal to minus 7, and then I give you x plus 3y equal to 4. Will the swapping make any difference in the solution set? I think it's fairly intuitive to know that just rewriting the equations in a different order will not change anything. So definitely if I swap something, nothing will change, and I will still have my solution set intact. What if I multiply one of the equations by a scalar? So what if I perform this multiplication by a non-zero scalar? Okay. What if I multiply one of these equations, let's say the top one, by a non-zero scalar? Will that have any effect on the solution? So for example, if I multiply the first equation by 2, so this will become 2x plus 6y equal to 8, and this will be 5x minus 4y equal to minus 7. Question now we are asking is, will this new system have a different solution than the first one? So think of it this way. What if I had given you this as my first, this as my system, original system? Wouldn't you agree we can just divide the first equation by 2 and we will be back into the situation without affecting anything? So in some sense you are just multiplying it by a scalar, so you're not changing the straight line that is being represented by this. So technically it will not make any difference in the solution set. So that means these two things, swapping of two equations, multiplying one equation by a non-zero scalar, should not have any effect on the system, on the solution set of the system. So now let us see what about one more operation. Let me try to introduce one more operation to this mix, and let us see what do we conclude about that. So our idea is to figure out, will the solutions be preserved under these operations? So two operations, one was swap, the other one was multiplication by a non-zero scalar. These two things we saw didn't affect our solutions. So what is another operation which might not affect the solution? So here is something which I propose. Let's see if we can do this and try to argue whether it will preserve the solution set or will it change the solution set. What if I did the following? I took equation 1, multiplied it by minus 5 and added it to equation 2. So this is my equation 1. This is my equation 2. What if I did something like this? So in some sense I'm trying to linearly combine two equations and see what happens out of it. So my first equation remains intact. That means I'm not really changing anything over there. I'm trying to do operations on the second equation in the manner that I have written over there. So if I do that, minus 5x will cancel 5x, so that is gone. This will be minus 15y and minus 4y. So then second equation will change its looks, and it will look like minus 19y. And on the right hand side we have minus 20 and minus 7 will give us minus 27. Okay. Now, from this system, using this operation, I have achieved another system. What I want to claim is, I want to claim that this system, the new system that I have got, whatever is the solution set of this guy, it would still be the same as the solution set of our original system. That is not at all obvious in this stage why that should be the case, unlike these two situations where things were more intuitive. But I will convince you in a moment that such would be a case. So let's first try to see how things are. What would be the augmented matrix of this new system? How will it look like? I have a 1, 3, and a 4. See, I am getting a 0. I am getting a minus 19, minus 27. It is not exactly the kind of dream matrix we were looking for, but it's kind of heading towards in the direction that we hope things will work out. So this is 1, 3, 4. Zero, minus 19, minus 27. Okay. Now, let's not worry about the final picture. Let's first argue that the solution set is going to be the same. What if I solve this? The second equation is so nice, you can directly solve from here as y to be 27 over 19. And once I have got the value of y, I can plug it in the first equation over here to get the value of x as 4 minus 81 over 19. Okay. So this would be minus 5 over 19. So x is minus 5 over 19, y is 27 over 19. If I use these two values of x and y, of course the first equation is the same as over there, so calculation error, it should work. Let's look at the second equation. If I plug in those values of x and y, what do I get? If x is minus 5 over 19, this will become minus 25 over 19. And since y is 27 over 19, this guy will become 4 times 27, which would be 108 over 19. So the left hand side will become minus 133 over 19. And minus 133 over 19 is nothing but minus 7. So, can we now say that at least whatever we obtained over there, the same thing satisfied our original system? This only tells you half the story. It just says that whatever is the solution for this guy also has the same solutions. But there is still a possibility this guy may have more solutions, and maybe we did not capture it over there. So now I'll convince you that those two systems are equivalent in terms of solutions. That means they have both exactly the same solution. Hence, coming to this form is a good thing for us, as we don't lose any information in doing these things. So I'll give you a geometric idea to convince you that such is the case. But once we have seen a geometric idea, it will help us understand this row operation better. Okay. Now, as you remember from the row picture of these equations, we know that these guys are lines, straight lines, and we are talking about the intersection of two straight lines. So if I try to plot these lines, so assuming I plot them correctly, this is the line x plus 3y equal to 4, and something like this is my line 5x minus 4y equal to minus 7. Okay. So I'm not plotting them to the scale, but once suppose I plotted them, you will see there is only one point of intersection, and we have already found that point of intersection. But my idea is slightly different. Remember, we had this new system of equation that I had got from doing that row operation. X plus 3y is equal to 4. Let me try again. And once I did that row operation, minus 5 times equation 1 added to equation 2, what we had got was minus 19y is equal to minus 27. Okay. Now this guy is also a straight line. In fact, this is a straight line, y is equal to 27 over 9. So if I draw this a straight line, then this straight line is actually a horizontal straight line that passes through this point, and this is our y is 27 over 19. As you can see, if you look at the intersection of the first two lines that we were originally considering, the intersection point was here, and if I consider this line and this line, still the intersection point remains the same. So geometrically we have a confirmation that, well, the intersection of these two lines is going to be the same as the intersection of these two lines. But how do you convince somebody algebraically that such is the case? So let me do a simple thing. Let me give these lines some names. Let me call this line as my line L1. Let me call this as my line L2. And let me call this horizontal line as my line L3. Okay? Now, how did I get line L3? Can I say I multiplied the equation for line L1 by minus 5 and added it to line L2, and that is how I had got my line L3. Now, if you allow me to write down the equations of line L1 and L2 slightly special way, that means everything on one side. So suppose I write it as x plus 3y minus 4 and L2 as 5x minus 4y plus 7. Okay. Now, I don't want to solve it because solving it is going to give me exactly this. I want to look at it slightly differently. Now, if I pick any point which lies on line L1, any point which lies on this line L1, I plug in the coordinates over here, this expression will become 0 because we are picking a point on L1, so it satisfies the equation of L1. Likewise, if I pick a point on L2, this expression will become 0 because all such points will satisfy equation for L2. Now what if I pick a common point, that means a point which lies on both L1 and L2, then can we say that both these expressions will become 0 at the same time for those values of x and y? And that would mean L3 also becomes 0. That means it will satisfy the equation for L3 as well. So that means if I solve this completely, what am I going to get? I'm going to get minus 19y plus 27. So whenever these two expressions will become 0, this expression will also become 0. That means any point which lies on both L1 and L2 will also lie on L3. And that is the reason why the intersection points of these two things will be the same as the intersection point of these two lines. Because each of these lines is a linear combination of the other two. And that is the reason why we were okay by just considering this system of equations. So the moral of the story is even this kind of a row operation, where I take a multiple of one of the equations and add it to another equation, even this will preserve the solution. And these three operations together, we call them as our row operations. So the third operation that we have found is as follows. It is multiplying one row by a scalar and adding it to another row. I should emphasize one thing over here right away. When I say multiplying one row by a scalar, note I am just saying it to be a scalar. I am not emphasizing it to be a non-zero scalar. So that means I am allowing the scalar to be positive, negative as it is 0. Of course, multiplying one equation by 0 and adding it to the another won't change that second equation. And if you notice, I have not used the word equation anywhere, I just called it a row. The reason for that is we want to get away from this equation business and only look at the augmented matrix. So everything has to be done in terms of rows and columns. So all these operations that we performed on equations, we will be able to perform them on the rows of our augmented matrix. And that is why we call these three things as elementary row operations. The word elementary may not be of much significance right now, but let's keep it so that later on when we see or when we use the term elementary row operations, you will see the significance of calling it elementary. Okay. So these are elementary row operations. That means these are the operations which, when performed on our augmented matrix, will not have any effect on the solutions, in the sense of it will preserve the solutions of the system. So let me try to use them to see if we can achieve the so-called final form of our matrix the way we want it. Okay. Now, remember we said we are going to use these operations to reduce it to a good form, and we had given that good form a name. We called it an echelon form. So let me first describe to you what is an echelon form. So first we should at least have the definition in mind. What is an echelon form? We will say a matrix is an echelon form if the following things happen. If all the zero rows the second thing is leading non-zero entry. Each row. The leading non-zero entry of each row is to the right of the leading non-zero entry of the row above it. Okay. So I'll write down some examples and we'll examine if these are in echelon form or not, whether they satisfy these two conditions. If they do, then we'll see how. If they don't, then we'll see a reason for them not satisfying these conditions. Okay. So here is my first matrix. Let's have 1, 2, 3, 0, 0, 0. Then let's have another matrix. 1, 2, 3, 0, 1, 0, 0, 1, 0. Then we have another matrix. 1, 0, 0, 0. Okay, so let's try to see which one of these matrices is already in echelon form and which is in. So let's start with matrix A. In matrix A, all the 0 rows are at the bottom. Well, we have a 0 row which is at the bottom. And the leading non-zero entry of each row is to the right of the leading non-zero entry of the row above it. So if you look at matrix 1, this is the first row. It has a non-zero entry, leading non-zero entry 1. There is nothing above it, so there is nothing to compare. And there is no other non-zero row. So it satisfies both 1 and 2. So both 1 and 2 are satisfied. So that means that this is in echelon form. Now let's look at matrix B. All the 0 rows are at the bottom of the matrix. Since it does not have a 0 row, so we don't have to worry about satisfying the first. It is satisfied by default. Now look at the second condition. The leading non-zero entry of each row is to the right of the leading non-zero entry of the row above it. If I look at this row, leading non-zero entry is 1. It is to the right of the leading non-zero entry of the row above it, which is okay, at least in this case. But if I look at row 3, the leading non-zero entry is here, which is not to the right of the leading non-zero entry of the second row. Hence, it does not satisfy the second criteria. So that means this is not echelon form. Okay, Now let us look at the third example. Again, there is no non-zero row. There is no zero row, so we don't have to worry about it. So the first thing gets satisfied automatically. The second condition says each non-zero entry of each leading non-zero entry should be to the right of the entry above it. So this is a non-zero entry which is to the right of the leading non-zero entry above it. This is a non-zero entry which is to the right of the leading non-zero entry above it. So it also satisfies this second condition. Hence, this is also in echelon form. So it is best to learn these definitions using examples and trying to make up your own examples. So now we know what is an echelon form, what is not an echelon form. And whenever we have an augmented matrix, our attempt will be to take that matrix, use row operations to get into its echelon form. You will learn how to get into echelon form also. But before we do that, I would like to introduce one more term in here. Let me just introduce the terminology once again. There is a slight difference between echelon form and what I'm going to introduce now. And they both have their own merits. So depending on what we are after, we will be able to find out what is the best form we are after. So the thing that we are going to describe now is what I will call as the reduced echelon form. Of our matrix. In short, I will like to call this as RREF, or row reduced echelon form of a matrix. So the thing which we studied before this one was echelon form, or sometimes we like to call it as the row echelon form. And this is the reduced form, or reduced echelon form. Okay. Now what is the criteria of something being in its row reduced echelon form? Okay. Let's try. So the definition is fairly straightforward, similar to what we saw earlier. So a matrix is in row reduced echelon form if, well, as the name suggests, it must be in the echelon form. So of course that part is taken care of. The EF part, it is in echelon form. What do I mean by row reduced? So this is the thing we want to ensure this time, that each leading non-zero entry must be 1. So we are not just saying that there should be a leading non-zero entry, but we are emphasizing that leading non-zero entry must be 1. And the third thing that we want is the column having the leading one should have all other entries as 0. Okay. So these are the three things that will make it a row reduced echelon form. So let us try to see in our example which one of these could be in its reduced row echelon form. Well, the first thing is it should be in echelon form. So one thing is clear, that if at all any of them is in the row reduced form, it could be only A and C, because B is not even in echelon form, so definitely it can't be in row reduced echelon form. So let's come back and see, what about A? It is in echelon form, fine. Each leading non-zero entry must be 1. Here is our leading non-zero entry and it is 1. And the column having the leading 1 should have all other entries as 0. The column having the leading 1, as you can see, the column having the leading 1 has all its entries as, other entries as 0. So it is, in fact, a row reduced echelon form. Okay. Notice we are only concerned about the leading 1 and no other entry in that particular row. They could be 0, non-zero, 1 or not 1, we don't care about that. This is definitely not echelon, so it can't be row reduced echelon form. What about this guy? This is echelon. Is it also row reduced echelon? Well, it's in echelon, that's good. Each leading non-zero entry must be 1. So here we have a leading non-zero entry which is 1. Here we have a leading non-zero entry which is 1. But here, the leading non-zero entry is not 1, and hence it is no longer a row reduced echelon form. So it is not row reduced echelon form. So one good thing about row reduced echelon forms is, if a matrix, if we try to reduce it to bring it to a row reduced echelon form, the final form will be unique if we insist on row reduced form. However, if we just insist on echelon form, there could be infinitely many echelon forms of a given matrix. And that is one reason why sometimes we insist on getting a row reduced echelon form, so that whenever I get, you get, or anybody else gets, it will be the same row reduced echelon form for a given matrix. So we'll encounter those things a little bit later. But from theoretical standpoint, if you just are looking in solving the system of equations, you will see echelon form is as good as row reduced echelon form from a theoretical standpoint. That means both of them are capable of giving us the solution. When it comes to computational cost, then you have to really balance things out. Because the advantage of a row reduced echelon form is, if you have a row reduced echelon form, it becomes easy for us to read the solutions immediately. So one would say, oh, then why not go for row reduced always? Well, if you want to go for something called row reduced, you have to do more row operations. So you are paying a cost ahead of time. And with the echelon form, things can be done with less cost in terms of matrix reduction, but when it comes to computing solutions, you pay the price there. So you have to balance it out, and depending on the needs, we would sometimes prefer one form over the other.